Hello, everyone. Welcome to the ILTA Physics online problem solving lecture. Today, we are going to solve problems about dynamics, the study of an object's motion and the force that causes that motion. The motion of an object can be explained by two things: the kinematic equations that describe the motion itself, and Newton's second law, which explains the cause of that motion through the relationship between force and acceleration. As you can see in the diagram, when a force is applied to an object, it creates a change in velocity, which means it creates acceleration. In today's lesson, we'll look at how to solve for the relationship between the force applied to an object and the resulting change in velocity. All you need to do is connect the various kinematic equations you've learned so far with Newton's second law, F equals ma. So first, let's quickly summarize the formulas we need to solve these problems. According to Newton's second law, the law of acceleration, a force applied to an object produces a change in velocity, which is acceleration. If there are multiple forces acting on an object, you must use the net force, which is the vector sum of all those forces. For two-dimensional motion, you can simply divide the forces into x-axis and y-axis components and calculate the acceleration for each direction. When a force causes a change in velocity, the object undergoes accelerated motion. There are five main kinematic equations used in this case. Since I explained the derivation and physical meaning of these formulas in detail during my theory lecture, I will just briefly review the formulas here. First, acceleration is defined as the change in velocity over the time interval. Using the definition of acceleration, the change in velocity can be calculated as the product of acceleration and time. If you know the initial velocity and final velocity, you can define the average velocity as the value in between. In accelerated motion, the change in position or displacement is expressed as a quadratic equation with respect to time. If you use the average velocity, you can also calculate it as average velocity times time. At this point, the final position of the object is the initial position plus this displacement. If the problem doesn't give you information about time, you can also use the relationship between displacement and velocity. Now, let's use these formulas to solve some basic problems. Problem number 9 describes the winter sport of curling. As shown in the diagram on the right, a player needs to push a curling stone with a mass of 20 kilograms on a smooth floor to make it stop exactly at a target 27.9 meters away. If the friction force acting on it is 2 newtons, what should the initial pushing speed be? To solve this problem, the first thing we'll do is set up a coordinate system and an origin. Since it's a one-dimensional linear motion, we'll use a Cartesian coordinate system where the right direction is positive, and we'll set the stone's initial position as the origin. Next, let's think about all the forces acting on this motion. In the sliding motion of this curling stone, the only force acting on it is friction force. Based on this, if you can read the problem and visualize the situation shown in the diagram below, you've already solved half of it. The most important thing here is the direction of the friction force. Since the stone is sliding to the right and coming to a stop, please note that friction acts in the opposite direction of the stone's motion, which is to the left. Now let's apply Newton's second law, F equals ma. Since the friction force acts to the left, F is negative 2 newtons. The mass of the stone m is 20 kilograms. Therefore, the acceleration EI is negative 0.1 meters per second squared. The reason the sign is negative is that the acceleration is acting in a direction that decreases the velocity. Now, let's find the initial velocity using the kinematic equation. We know the displacement, which is 27.9 meters, but we don't have information about time. So we use the time-independent formula called the velocity displacement equation. Since the stone must eventually stop, the final velocity v(f) is 0. If we plug the acceleration of negative 0.1 into the equation and calculate it, the initial velocity comes out to 2.36 meters per second. It might seem like a simple problem, but it is essential to practice correctly plugging in the directions and signs of force and acceleration according to your coordinate system. Problem number 12 deals with a situation where a 50-kilogram box is being pulled by a rope on a frictionless ice rink. In this problem, we need to find the tension in the rope in 3 different scenarios. This is a very basic type of problem to check if you accurately understand Newton's second law, F equals ma. Let's calculate the tension for each situation. First, if the box is at rest, it means there is no change in velocity at all. Since there is no change in velocity, the acceleration is 0. Therefore, if we plug this into the equation, the tension on the rope is 0. Next, we should notice that although the box is moving at a speed of 5 meters per second, the velocity is constant. The phrase steady velocity or uniform motion means that the acceleration is 0. Since acceleration is 0, in this case as well, the tension in the rope is 0 newtons according to F equals ma. Many students mistakenly think that force is required if something is moving. But please keep in mind that the net force is 0 during constant velocity motion. Finally, let's look at the case where the box is moving and accelerating at the same time. In this case, since there is acceleration, actual tension finally occurs in the rope. According to the formula, if we multiply the mass of 50 kilograms by the acceleration of 5 meters per second squared, the tension is 250 newtons. The key to this problem is understanding the principle that if there is no acceleration, the net force is also 0. Whether an object is stopped or moving at a constant speed, please remember that if there is no acceleration, the net force, the tension, acting on that object becomes 0. Problem number 14 is a car crash situation. As shown in the diagram on the right, a car traveling at 14 meters per second crashed into a wall and stopped in 0.1 seconds. Fortunately, the driver, who weighs 70 kilograms, was wearing a seatbelt. How much force did the seatbelt apply to protect the driver? Again, using a Cartesian coordinate system, let's set the right direction the car was moving in as the positive direction. The car was moving to the right, the positive direction, and stopped upon impact. So the acceleration acts in the opposite direction of the motion. According to the definition of acceleration, if we divide final velocity 0 minus initial velocity 14 by the time of 0.1 seconds, the acceleration is negative 140 meters per second squared. Please note that it has a negative value because it is in the direction of decreasing velocity. Let's calculate the force that created this acceleration, the force the seatbelt applied to the driver, using F equals ma. If we multiply the mass of 70 kilograms by the acceleration of negative 140, we get negative 9,800 newtons. The negative sign here means that the seatbelt applied force in the backward direction to prevent the driver from being thrown forward. Since the problem asks for the magnitude of the force, you can answer 9,800 newtons, excluding the sign. Today, we applied the kinematic equations and Newton's second law to real-world problems. The key to solving these problems is accurately understanding the directions in which velocity, acceleration, and force act, and determining the signs according to the coordinate system. That's it for today's lecture. Everyone, you did a great job. I'll see you again next time.